Okay, think about the most extreme machines we build, the ones that operate on the very edge of what's possible. They're made from materials designed to be, well, almost indestructible. So how do you shape them? Today, we're unlocking a secret recipe for taming one of the world's toughest supermetals.
So what is this stuff? It's called Inconel 718. It's a nickel-chromium superalloy that basically just laughs at insane temperatures and pressure. And where does it live? Right in the heart of a jet engine. This is a place where failure is just not an option. I mean, the stakes, they literally couldn't be any higher. All right, so that's the setup. You've got this incredibly tough metal, and you need it for something critical. But here's the real puzzle, the multi-million-dollar question. What if you only need one? Just a single prototype for a new engine design. How in the world do you shape something so stubborn, so resistant, without building a whole massive factory for just one part? And this right here, this is a massive challenge for engineers and designers. It's what's known as the prototyping problem. So let's break this down. The difference here is just huge. On one side, you've got mass production, the old way. Imagine a giant custom-made stamp that just smashes metal into shape. It's awesome if you're making thousands of parts. But for just one prototype, the cost of making that giant stamp, those custom dies, it's absolutely astronomical. It's just not going to happen. Right. So the old way is out. We need a new way, a smarter, much more flexible way to form this kind of metal. And here it is. It's called incremental sheet forming, or ISF for short. And you gotta forget those giant stamps we were talking about. Instead, I want you to picture something more like 3D printing, but for a sheet of metal. It's this really clever die-less process that uses a simple little tool, all guided by a computer, to slowly but surely shape the material. Okay, so how does this magic actually work? Well, first, you take your sheet of Inconel and clamp it down tight. Then, the computer takes a 3D model and maps out a path. And here's the cool part. A small, rounded tool just follows that path, pushing into the metal. It's almost like a pen, drawing a 3D shape right into the sheet, pass after pass, until, boom, the final shape is there. It's super precise, incredibly flexible, and, best of all, it's actually affordable for just one part. But you knew there was a catch, right? Because a brilliant idea is one thing. Getting it perfect, that's a whole other story. And remember, we're talking about jet engines here. Perfection isn't just a goal, it's the only standard. See, the problem was that the first parts made this way, they just weren't perfect. Not even close. The surface finish was rough. The metal would actually spring back a little after being formed, messing up the whole shape. And this is the really scary part. The walls could get stretched so thin that they'd risk failure. And we're not talking about little cosmetic blemishes. In a jet engine, any one of those flaws is a potential catastrophe. So, to fix this, researchers went to work. They set up an experiment, basically trying to find the perfect recipe. They had 3 main dials they could turn. How fast the tool moves, that's the feed rate, how deep it pushes with each pass, the step depth, and the viscosity of the lubricant they were using. And the whole game was to see how twisting these dials changed the things that really mattered. That surface roughness, the accuracy of the shape, and the thickness of the walls.
So they ran a whole bunch of experiments, 20 in all, basically hunting for the pattern, the key that would get rid of those flaws, and finally crack the code for a perfect part.
And after they crunched all the numbers, after all that analysis, they found something pretty incredible. All the dials made a difference, sure, but one of them was way more important than all the others combined. Yep, the study found the master variable, the one dial to rule them all. It was the step depth. Turns out, how deep that tool presses into the metal on every single pass, that was the key. It controlled everything, the roughness, the accuracy, and the thickness. And you don't have to take my word for it. You can see it right here. Just look at the statistical impact. Step depth absolutely towers over everything else. The feed rate, and especially the lubricant. I mean, it's not even close. This was the secret they were hunting for. The key to this whole thing was hiding in plain sight, in that one simple setting. But why? I mean, why is that the secret? Why does making that one little adjustment, a smaller step depth, have such a massive impact on the finished part? Well, it all comes down to the physics of what's actually happening. Okay, here's the breakdown. When you use a smaller, shallower step, the tool's path overlaps more. And all those little overlaps act like a polishing effect, which gives you that super smooth surface. That's number 1. Number 2, Each push is gentler. That means less energy gets stored up in the metal, which means way less of that annoying springback. You get a much more accurate shape. And finally, because you're not stretching the metal so aggressively with each pass, the walls stay thicker and stronger. No more dangerous thinning. So now they had it. With that master variable unlocked, the researchers could finally write it all down. The one optimal recipe for perfectly shaping Inconel 718. And this is it, the holy grail. The perfect recipe is a fast feed rate. We're talking 3,000 millimeters a minute. Then a really shallow step depth, just 0.2 millimeters. And finally, a medium viscosity lubricant. That's it. That's the exact set of instructions you need to take this wild, unruly supermetal and turn it into a flawless, high-performance part. And what do you get when you follow that recipe? You get the trifecta of quality. You get the smoothest possible surface, you get maximum accuracy with no springback, and you get the strongest, thickest walls for ultimate safety. All three problems solved. And this is the real takeaway. This is why all of this matters so much. This is way more than just a cool science experiment. This recipe literally unlocks on-demand manufacturing for some of the most critical components in the world. You can now make reliable, custom parts whenever you need them, without having to build a giant factory. So it really makes you wonder, right? If we can find the perfect recipe for something as tough as Inconel 718, what other materials are out there? What other so-called unformable materials are just waiting for someone to find the right recipe and crack their code?